Welcome to our Diving Dynamics video report. Our group consisted of Ensign Lynn, J.B. O'Neill, Jonathan Behringer, and Vishnu Reddy. Here's a brief description of our project. The main objective of this project is to model an Olympic diver using dynamics concepts covered throughout this course. We primarily use MATLAB as the software to record each calculation process and create visualizations of each phase. We then created a report after each phase describing what tasks were given and how they were completed. All of the code is attached and contains comments which explain the purpose of the code. For our quote-unquote diver, we used a model human as seen in the pictures. The total mass was 60 kilograms and the total height was 1.8 meters. The first image shows the dimensions of each body part as a proportion of the total height, h, which were used in the center of mass calculations. The second image gives the center of mass and the moments of inertia for the straight position. The final bullet point gives the mass of each body part as a percentage of the final mass, m.
Throughout this project, we worked with 3 different orientations: open, pike, and dance. For the open orientation, arms are extended straight upwards. For the pike orientation, the legs are open from the torso and by the arms. And finally, for the dance orientation, the arms and legs are off-centered in opposite directions when they are rotated about 30 degrees about the x-axis. The calculation for the center of mass is fairly straightforward, and it's shown in slides here, but we utilize SolidWorks' ability to calculate these values by creating the models in each position as described by the dimensions of the Dynamics PDF, and this saved us quite a bit of time.
In phase 1, we were first tasked with finding the center of mass and moment of inertia matrix for all of the orientations. We modeled the original straight position to show that our method of modeling each position in SolidWorks would allow us to find the center of mass and the moment of inertia of other orientations. As seen on the right, the center of mass and moment of inertia values calculated by SolidWorks match the given values from the project description once the mass, total mass m, and total height h values are multiplied in.
Next, we created the models in the open position, which we used to find the following center of mass and moment of inertia matrix. The main points from this result is that the center of mass only has a component in the y direction due to the symmetry, and that there are only IXX, IYY, and IZZ components in the moment of inertia matrix. Note that IXY, IZ, and IYZ components are all 0 as a result of the symmetry within. On the left is an image of our SolidWorks model compared to the image given to us in the Diving Dynamics PDF. Following that, we then modeled the pike position where putting the legs and arms in front added an X component to this infinite class. This results in the addition of IYX and IXY components in the moment of inertia matrix, but the IXZ and the IYZ components still remain 0 as a result of the symmetry in the relevant plane. Again, on the left are our pictures of our SolidWorks models compared to the image given in the Diving Dynamics PDF. Finally, the last orientation we have to model is the dance orientation. The rotation of the arms and legs about the x-axis created a Z component in the center of mass. This results in the IZ and the ICY components appearing in the inertia matrix. The IXY and IXZ components are 0 due to the symmetry of the body again. The SolidWorks models are captured on the left along with the picture of dance position from our Diving Dynamics PDF.
To find the initial velocity, the kinematics equations of projectile motion were used. Without being given a value for time, the first equation was the only one we could use to find initial velocity in the y direction. The second equation is just the first after solving for the initial y velocity, as the final velocity would be 0 for the section of the dive from the start to the maximum height. With this value now known, and the max height given value of 3 meters above the starting position, we use the third equation to calculate the time it takes to reach the maximum height. The fourth equation is once again the general equation after solving for t. As we know the distance to the point where the diver returns to the starting height, We can use this and double the calculated value of t to find the initial x velocity using the last equation shown. Taking the magnitude of the two components of the initial velocity gives us the total initial velocity of the center of mass.
Another one of the conditions that we need to find for phase one is the angular velocity of the body, or at least the initial angular velocity. We can do this using formula seen here on the right, where the angular velocity is a function of the change of rotation over the change of time. It is given to us that the rotation of the body is pi radians, or 180 degrees, during the dive, so we need to calculate the time. We once again use kinematics to find the time, first for the portion going up to the maximum height, and then again for the freefall portion towards the water. With the total time of the dive being 1.91 seconds, the angular velocity for the dive was found to be 1.6281 radians per second initially.
For phase 2, we had to describe the motion of a more complicated dive in 3 dimensions. This dive, known as 105B, incorporates transitions and different positions. We assumed that the transition between states was linear to simplify the computation. During this dive, we were given a breakdown of how long the diver stays in each configuration and were left with the above information, where for the first 10% of the time, the diver is in the open position. For the next 10%, the diver transitions to the pike position. For the next 60% of the time, the diver stays in the pike position. For the following 10%, from 80 to 90%, the diver transitions back to open, and the final 10%, the diver stays in open. Because the diver is changing orientations, our moment of inertia matrix does not remain constant. Thus, we need to find the moment of inertia at different points. We wrote a code to interpolate the changing moment of inertia, assuming linear transition between the states.
For phase 2, we were tasked with finding the linear velocity and acceleration, as well as the angular velocity and acceleration components of the center of mass. We solved these using the kinematic equations and acquired the following graphs. The velocity of the center of mass for the diver remains linear throughout the dive, and we can see this in the trajectory as simply parabolic. The acceleration is constant, so we did not put a graph here, but it would just be a flat line at negative equidistant, which represents gravity. The angular velocity and acceleration of the center of mass changes in the direction of their orientation. This could be seen in our graphs on the bottom. Note that we treat the diver as a rigid body so that the angular components of the torso are equivalent to the angular components of the head. This will be used in future calculations to get the velocity and accelerations for the center of the head. The velocity and acceleration components of the center of the head are different from the center of the mass due to the rotation of the body as the diver. We utilize numerical methods in order to solve the velocity and acceleration components, and as such, do not really have to mess with ordinary differential equations. Because of the flips during the dive, we see a cyclical pattern in the x and y velocity and acceleration. And if we think about the orientation of the head and the velocity vectors during the dive, this makes sense, as during the flips, the velocity vectors of your head would be pointing towards the back, and then they will come back towards the front as you finish your dive. Our objective for phase 3 is somewhat similar to phase 2 in that we are modeling the dive, but this time we want to incorporate advanced maneuver into our mix of moves. We need to create a visualization for more complex dives, as well as create an optimization to simulate perfect. In order to do this, we first need a defense. Our diver is changing positions during the dive, which results in a change in the moment of inertia matrix due to the shift in mass distribution. By applying the conservation of angular momentum and keeping in mind Newton's equations for 3D dynamics, we are able to numerically solve for the angular velocity and angular acceleration for every point in the dive. Since the moment of inertia matrix changes, we need to interpolate to find the intermediate values of the moment of inertia matrix. But because we created our function to interpolate the moment of inertia matrix in phase 2, we could simply use the same MATLAB script to run phase 3. From our numerically derived equation, we acquired a vector of values for rotation, angular velocity, and angular acceleration in all three dimensions and graphed them over time as shown. Note the eccentric nature of the graphs as the diver changes positions during the map. On the top right are the results of the rotation of the body for optimized quote-unquote kick math. It appears to be very similar to the original dive with some minor tweaks. Much of the code that we created for phase 2 could still be applied to phase 3. We just needed to change the initial conditions slightly. Due to this, we were able to get away with not having to rewrite our entire code, saving us a lot of time.
The general process for visualization involved getting the numerical data from the code from the previous phases of the project and running a huge for loop through it and essentially just extracting the data that we need. So we'd have a bunch of angles and positions with respect to time, but we'd run a for loop through all of them and plot all of them on one nice graph. And they're all numerical solutions. They're all numerical values that were all evaluated as a function of time. But yeah. So this just shows some of the evolutions of our visualizations. As you can see, we start off pretty simple. Phase 1 and 2 were both just 2D. And phase 1 also didn't really have any changes in the angular velocity of the rotations. But you can see that phase 2, I did have to kind of adjust how much the diver rotates depending on their position. And then for phase 3, you can see that it not only rotates in one axis, but also in the other two as well.
In conclusion, we learned many things from this project. First, Euler's equations are powerful dynamic equations which can be used to model and predict the motion of bodies in 3 dimensions. Secondly, we learned to utilize software to our advantage when simulating motion. Software such as MATLAB and SOLIDWORKS were invaluable in solving the equations we had in order to perform our simulation. Overall, we learned a lot about collaboration and problem solving and had an experience with this project.